Hello again. Today we're going to talk about calculating clearances on CRRT. But before we do that, I should let you know that you're going to need to understand how CRRT works before you understand how to calculate clearances. So we're not going to go over the mechanism of CRRT and how it actually works. There's another tutorial for that. But if you've seen that tutorial or you already have an understanding of how CRRT works, then we can move forward and teach you how to calculate some simple clearances. So what we're going to do first is draw a simple schematic of a CRRT machine. Here's your filter, and we're going to have some fluid come in, and so we're going to use some different colors here. And let's change this around. And one more color, and then we'll define what all of this is. Now what I've depicted here for you is a CVVH machine, continuous venous hemofiltration, and let's annotate these arrows. This is the blood flow coming in and going out, and we'll label going out as Q prime blood flow. This is your replacement fluid. This is called pre-filter replacement fluid, and in the prerequisite lesson you'll have an understanding of why we use pre-filter replacement fluid and not post-filter replacement fluid. And this is your effluent, all the stuff that comes out of the system that you discard. So this is a CVVH simple schematic, and of course in CVVH you're relying on convection to eliminate solutes, and therefore you have to calculate a convective clearance. So we're going to say clearance of a solute X, and we're going to call this convective clearance. There you go. So we want to calculate this entity here. Now, to do clearance calculations on any patient who's receiving CRRT, you have to know or assume two things. And the first thing is that CRRT takes a long time, meaning the equilibration that occurs between the fluid that you give, the replacement fluid, and the blood takes a while to occur, anywhere between 12 to 24 hours. And the second thing that you have to know is that equilibration will occur if you give CRRT enough time. We're going to use these two principles to come up with an equation that will be quite simple, as you'll see on the next pane. Alright, so let's go through the actual clearance equation and try to figure out what all the different variables mean. So let's draw this schematic again. This is our CVVH machine, where clearance only occurs through convection. This is the blood flow coming in and the blood flow going out. We have a replacement fluid that we put in pre-filter, and then we have an effluent. This is all the stuff that's removed. QEFF is effluent. Okay, so we know that clearance equations generally take the following form. Clearance of any substance is equal to the volume times a ratio of the concentration of that substance in the fluid. So we'll say let's write it this way so it's easier for you to understand. In the fluid divided by that same concentration, but in the plasma. And this is the general architecture, the general format for any clearance equation. You've seen this in different forms when it comes to peritoneal dialysis, and you're going to see it right now being applied to CVVH. So let's look at convective clearance. Now, clearance here is all convective because it's CVVH. There's no dialysate fluid running in the opposite direction of the blood flow. So let's look at the volume. Well, the volume is really just the effluent. That's what comes out. You can look at effluent as the urine that's being produced by the CVVH machine. And it's okay that we're using flow of effluent, in other words, volume over time, because we're going to be using that throughout this entire equation, and so you'll keep the units of volume over time, which is what you want here in clearance. So the volume is just your effluent blood flow, and we're going to describe what that is in a minute. And then you've got a ratio of the compound, and let's say that compound is X in the effluent over X in the plasma. So in essence, this is your clearance equation. Now, this may not be what you use in clinical practice. We're going to clean this equation up a little bit, but this is the general structure for convective clearance equation when you have got a patient on CRRT. Now let's clean this up a little bit. Let's draw this one more time. Alright, so this was the equation that we were left with, convective clearance of a substance in the effluent over that same substance in the plasma. Alright, so let's clean this up. First, we know that over time, the concentration of any substance in the effluent will approach the concentration in the plasma. In other words, the concentration that you provide of that substance in the replacement fluid will be the concentration in the blood or the plasma over time. So that makes this entity equal 1. And that's why you can cross this entity out. They will cancel each other out because over time, concentration in the plasma will equal the concentration in the effluent. So then you're left with simply this. Now, what is your effluent? Let's talk about that. There's a lot of things that come out here. First, the effluent is, in part, your replacement fluid, plus anything extra that you remove from the patient, and that's known as ultrafiltration. Or let's label it this way. Since it's coming from the patient, let's color it red. There we go. So your effluent is really your replacement fluid and whatever extra you remove from the patient, your ultrafiltration rate. Now you set this, so you know what this is, and you also set this. And so you have a way of calculating your effluent by simply adding these two parameters together. Now that would be the end of the clearance equation, except for the fact that you've put your replacement fluid pre-filter. In the previous tutorial, the prerequisite tutorial, you have an understanding of why a pre-filter replacement fluid strategy is different than a post-filter replacement fluid strategy. The equation you have here is one that will calculate your convective clearance if you had your replacement fluid post-filter over here. But since you don't have that, you have a pre-filter replacement fluid strategy, you're going to have to add into this equation a fudge factor. So your clearance is going to be your Q effluent times some fudge factor. The reason you have to have a fudge factor is simply because the blood that enters the filter at this point right here does not have the same concentration of the solute as it does out here, because you added replacement fluid, because you diluted the concentration. And so you've got to take that dilution into account, and that's what that fudge factor is for. You don't need a fudge factor when you have your replacement fluid placed post-filter, because you're not diluting anything. And so you just have to remember what this fudge factor is. And so let's go through it. It's very easy. It's your blood flow divided by the sum of your blood flow and your replacement fluid. So in the end, you get an equation that looks like this. And there you have it. That is your formula for convective clearance in CRRT. Thank you very much.